Okay, I think I'll go ahead and get started here and people trickle in if they can. Good morning, all. My name is James McVeigh, and I'm one of the developers in Tsdat. It's an open source data pipeline code we use to read, process, run quality control for raw data in standard formats. This webinar, I'll be going over how Tsdat can be used to create data pipelines. It can be for marine energy or any industry. And I'll start with some slides going through background motivation goals of Tsdat, as well as an overview of just a basic pipeline setup. We'll have some survey questions for the audience that Haley will give out, and we'll jump into a demo about how to run a pipeline. I'm going to close my screen to stop my video to run through the PowerPoint. We'll get started. So what is Tsdat and why was it created? I'm sure many of you have worked with a range of different instruments and DAC systems, and it seems like not a lot of them output data in the same way. If they do, it might be some format, some binary format. A lot of mini DAC stuff, especially now, is working in TDMS and some of HDF5. They always store variables, it seems, in a different way. Then you have to write up some code script to organize, check that data. Usually if it's some MATLAB format or some HDF5 format, you have to figure out how the data is structured, different channels and groups. Once you finish data wrangling, then you can finally get started on analyzing that data and getting it to a format that you can share or upload to the cloud. And if you're like me, hopefully someone will find that data useful. In a study conducted by Anaconda, which is a data science platform, they found two things. Half of most people's time is spent on data wrangling, and none of them like it. So the motivation behind Tsdat was to build a common code structure to decrease the actual amount of time you spend on data wrangling, on the steps of getting data to the point of actually analyzing it, and two, to output data in a common, what we'll call standardized format that everyone can understand and that's easy to share. In practicality, this translates to providing an open source data pipeline to actually allow users to relatively easily process their data that can be stored in the cloud. For marine energy, this is MHKDR, the Marine Hydrokinetic Data Repository. I'm sure many of you know about where exists a pool of data that anyone can draw from. So the hope for MHKDR is to have a common source bank for if it's something like environmental monitoring, this means having a database of stressor research. So it's fish collision, passive acoustic monitoring, EMF, light, etc. For marine energy research, this can be anything from resource characterization, environmental data, to parametric structural loads, especially model forecasts, hindcasts, and to further use that data to extend it to further modeling, data mining, or just where we can have a common community to help push marine energy to further the field. Tsdat's approach follows that used by the Atmospheric Radiation Measurement Research Program. That's ARM. That's the wind side, the atmospheric side of DOE research. We want to include a lot of the same features that they have in their pipeline setup, which comes down to storing metadata, being able to support any size, shape, and data format, observational model data. These can often have different formats and setups, and include visualization tools so you can run the pipeline and see what's happening as it's moving along. This also includes defining baseline standards that can be extended to any domain, so not just climate or marine energy, and to keep the code base framework light and flexible, again, so anyone can use it, and make sure these all can be shared. Especially the point on key components to be contributed and shared by the community. This way, if someone has a function or service that's applicable to a particular instrument or system, other users then won't have to reinvent the wheel, and we can again save time. I mentioned data standards earlier at the beginning, and what I mean by data standards is this is simply the metadata that is the provenance, the description, the quality control. Provenance meaning where did the data come from? Description being what is this data, quite literally, how was it used? Quality control, was there any despiking? Was there max and min checks? What data is missing? So typical, like this is what you want from a standard data set that you might not have in the raw data, if that's just a simple matrix or a CSV file. This, of course, comes with standard unit names. If you're naming something speed versus velocity, something's in degrees Celsius versus C. And finally, of course, data standards. They are different among some industries, and we wanted to conform to that as well. So that was a quick run through of the idea behind Tsdat, and I'm going to run through how we decided to build it. So we did so with the approach that data can be organized in a hierarchical fashion. This may be different from what you're typically used to seeing data as, but this is simply structured that raw data inputs are at the low end of the tier, and finalize what we're calling high-value data products are at the end of the tier. High-value data products is the stuff you're actually going to use for your analysis. The development processes that bridge tiers of data are what are called data pipelines. The completed Tsdat framework as of now is the ingest pipeline. That's what's in the red box here, and that bridges the first gap between raw data coming off an instrument or data acquisition system to standardized quality controlled data. Future Tsdat development will focus on the VAP pipeline here, VAP standing for value added product, to take this standardized data and apply additional algorithms. What these algorithms could be, it could be something simple like calculating salinity from a CTD, or converting time series data into the frequency domain. Maybe you want something for spectral analysis, or something a little more complicated like synchronizing time across multiple instrument data streams. But for now, Tsdat is focused on converting raw data to standardized data, and we hope to get up the VAP pipeline in the future, because this is really where value is added. So Tsdat is set up so that researchers can download a pipeline template from GitHub and customize it to your needs based on 3 sets of files and classes. The first and one required level to have a running pipeline is to fill out configuration files. These files define where the input's read from, what variables are required, what metadata will be stored. Quality control algorithms can also be specified here. And finally, storage. Storage refers to if you're just running it on the PC, or if you're running it to the cloud, AWS or Azure, and that data is all stored in these files. The second level of customization are additional function hooks, as they're called, that can be run at various points in the pipeline. The first 2 functions are useful for adjusting or recombining raw data if need be. Say if you have 3 entries for a variable like speed, maybe you have speed in the XYZ directions, UVW, you want to combine these into a single variable called velocity, you could do that here. The final hook is specifically tailored as a space for data visualization. So any plots you can create, you specifically pulled out aside to do those there. The third level of customization is what are called helper classes. Tsdat has many of these built in, but these are the modules that can be shared across pipelines. They include file readers. This is what you're taking off an instrument or a DAC, what you're essentially translating maybe it's a proprietary binary format or like TDMS file into something that Tsdat can read. Data converters, these are something like unit converters. Quality control functions are also done here. Tsdat has a lot of these built in. In a lot of cases, there are some custom ones that you may want to run. And finally, data writer is quite what it sounds. This writes the data to the output file, which in the case of Tsdat is either a CSV or the netcdf file format, which if you're not familiar with netcdf, it's a file format that the climate community came up with that is useful for multi-dimensional data and especially useful for geospatial data. So if you have something like latitude and longitude as your 2 dimensions, and you have a slice or a raster of temperature data, it's essentially organized where you can have 3 dimensions of latitude, longitude, and then your temperature data. So Tsdat supports this NetCDF format, which can be especially useful in the marine energy sphere. And so now if Haley wants to do some quick survey questions, I just want to gauge the audience, what our understanding is for the demo that's coming up. These will pop up and you just answer them. It shouldn't take too long. And please flag in the chat if you can't see the survey questions. I'll give you another minute to get answers in. Quite varied across the board, it seems. Okay, thank you for that. So for this demo, I am going to use VS Code. I see that a number of people are not so proficient in it, but you can run Tsdat in any IDE you prefer, whether that's PyCharm or Spider. So with that, I'm going to leave the PowerPoint. And I'm going to switch over to the demo. Reshare my screen. Share. So to start, to get to Tsdat, you can pretty easily find it by searching Tsdat GitHub. You can click on the first link. This will bring you to the main repo page. And what I want to come overview here is there's the Tsdat source code, which you don't particularly need to worry about. The pipeline template. This is what you're interested in for building a pipeline. And then finally, you can access, well, I'm going to open the source code. You can access the documentation by going to Tsdat, read the docs to that link. But to go back to the main page, to download a template, you can simply click on this link. You'll have to create a GitHub account to do this, but you want to click use this template to create a new, this is essentially going to store your pipeline on your GitHub. And I'm just going to name this pipeline webinar example. You might want to switch this to private and create repository. It'll take a hot second to create this under your GitHub account. And from here, you can either clone it through GitHub, or if you clone it through Git, excuse me, if you don't know how to use Git, it's quite simple to download the zip folder. And then from this, you can open it up in the IDE you prefer. In this case, I'm using VS Code. So what this will open up within this folder are a number of files that are fully contained in the pipeline. If you would like to know how to set up and run your own pipeline, do all the configuration, I'd encourage you to go to the documentation and work through the tutorials. But for now, I'm just going to show I'm going to show the input data. I'm going to show what happens when the pipeline runs and what you expect to output. So this input data is a simple CSV file. This comes from some buoy data from the Axis buoy off the coast of Humboldt. It's just a short clipping, but this is a simple CSV where you have a header file with, you have your header with your variable names. This is wave data. So this is related to wave displacements and wave heights and periods, if you're not familiar. And then you have the standard time column along with all of your data. Not all of it is here, some of it is missing. And so to run this through Tsdat and VS Code, I'm going to open up a terminal. The pipeline is run from the command line. It is quite simple. Python runner.py. Runner.py is the command file. And then you're going to give this an entry of your the path to your data. In this case, it's the CSV file. So it's Python command data. So when I hit go and hit enter, this will output a few lines here. It'll give you some info lines. This is telling you that it saves a couple things in storage and that the pipeline succeeded. What this does, it creates a second directory within your main folder called storage. And there's two folders in here. There's ancillary and there's the data. So ancillary shows the plots. I'm going to close the terminal. This is a plot of this wave data. Notice there is some missing. And again, if a variable is missing, it won't show up on here, which is why we're missing some direction, some period data. And the second plot I created was of wave height and a subplot of the QC. So this QC block shows the three tests I ran on this. There was if there's data missing, if data is less than the range, less than what the valid range I expect, and more greater than the valid range. So missing data will be flagged under test one with this bar. And data greater than the range I specified. In this case, I did not expect wave heights above 20 meters. That was also flagged. So what this output data actually looks like in this CSV is quite similar to the one we input. In this case, there's the header column where the variables here are renamed. We have the data once again in the same place. I did not do anything to the missing data. I did not interpolate any of this, hence it's still missing. And it adds additional variables and additional QC variables. All the 0 corresponds to nothing happened. 1, this is the first bit where there was missing data, and other bits will show up as different values here. So for CSV files are quite limited in what they can show, hence the netcdf I brought up earlier. Netcdf is saved as .nc. I realize many people are not familiar with this. So also in this pipeline, we include a Jupyter notebook. If you're not familiar with Jupyter, it is a very good way to learn Python because it handles everything in the background that you don't need to run. So this notebook will pretty much open up the netcdf file we created once it connects to my Python terminal, and I can show the full value of the MEData pipeline using Tsdat through the netcdf file. So what this does, this is a relatively simple file because it has a single dimension, time, and all of our data variables and all of our metadata, all the attributes, where we have title of the data, description, where it came from. And then within each of these variables, we have let me pick up one that actually shows data. We have the data that is actually there, significant wave height, there we go. And then we have the additional metadata saved on top of this. So we have the units, we have the name, we have any QC attributes here. This is set to 20. And then our other QC variables that are stored along with this, which is significant wave height. Let me pull up one that actually has, this is one that has some QC bits flagged. You can see there's the 4 there for, if I look in this metadata, 4 relates to one of the flag masks. So in the QC, this flag mask of 4 corresponds to this next flag meaning value greater than the valid range. So this can all be useful to someone who's never seen this data before, who can open up data and be like, okay, does this look okay? Does that look okay? And then actually look at the QC and be like, okay, that's what's going on, which is a lot more informative than if we just have some raw data with the original naming scheme, where if you don't know that ZCN stands for zero number of crossings, you might not guess that. So with that, that is the quick demo I wanted to run through. If we have any questions, please put those in the chat. There is much more to Tsdat in this quick demo, so I encourage you to look at the tutorials, and please reach out if you have any problems or issues. With that, I'd like to open it up to questions. We can, I believe, Haley, we can put those in the chat. Otherwise, thank you for coming, and I hope you enjoy the rest of your lunch if there are no questions.
So just want to let everyone know that this has been deployed for other domains, and we are starting to process some data within the marine energy domain as well. So if you have relevant questions, looks like everybody would use this if the service was available. If you want to talk a little bit about the problem space or your data set, this is a great time to talk about it. There's one in the chat, James. What's the advantage of running it in VS Code? Why not run it entirely in Jupyter Notebook / Python?
VS Code just has a greater, I'm unmuted. VS Code just has a wider ability for a user who really wants to integrate Tsdat into their full pipeline, especially if they're running in real time into the cloud. Max, you'll have to correct me if I'm wrong, if you can run it in Jupyter Notebook. But I'd say that's the quick answer.
I can also answer. We set it up as a pipeline so that this can be integrated with MHKDR. So as data gets uploaded, the raw data gets uploaded, we run it through the pipeline and make it available as an ingested data or standardized data. So that's how we envision it. There are 2 use cases. One is being used as a pipeline, and the other being used as researchers. They just want to analyze data. So, so VS Code is one way for developers to, use the entire pipeline and see the various parts of the pipeline and make some changes, and then deploy it on AWS. Great question by Paul. Does Tsdat currently support ingestion and standardization of image and video data?
That is a good question. No, it does not.
Does not.
One shortcoming I will say that I'm interested in getting around is the support of wave data from passive acoustics. The wave format is just a very efficient way of storing sound data, and I think it may very well be the same way with JPEGs and MP4. I know MATLAB does carry schemes for image data where you can edit the raw RGB, but currently no, we don't support that ingestion. That's a good question, Paul. Thanks.
We could add additional hooks to the pipeline to process that data, right? So for
It's an
ARM,
interesting question. We just haven't had the use case yet, but
yeah.
it is a good point for monitoring for wave energy devices.
Great, thanks, Bob.
Yep, thanks. I'd be happy to. We'll stay on another minute if anyone else has any other questions. Otherwise, please enjoy the rest of your day. Thank you for your time and attention. It was much appreciated.
If you have data that needs to be standardized and processed, please do reach out to us. We can get you started. James, are you seeing the question?
I do, from Sandra.
Yeah.
No worries. Let's 30 layers of measurements each 10 minutes. I think that's a good question for offline. That could be complicated. But so Tsdat should be able to handle if there is missing data like that. And oh, I see what you're saying. Yeah, Tsdat will be able to handle if there is missing data. You simply tell it for the QC, it can ignore that. If that kind of answers your question. Otherwise, yeah, please reach out afterwards. Because I do use Tsdat to work with the ADCP processing that I use. But that is a good question.
And we have dealt with this with the ARM program as well. When there's a ship deployment and all the sensors are on the ship, we had to deal with pitch and the roll and had to deal with correcting the movements as well, the ship movements as well. And we can point you to some example ingests that we have been done, Sandra. Mm-hmm. Yes, we can definitely help you with that. Do you have data that needs to go into MHKDR currently that needs to be processed? I'm going to put the distribution list where you can chat with us through that. Let's see. Process this every time.
Yeah, just shoot us an email. We'll
Yeah, we will help you.
further discussion. Okay, thank you all for coming. Please enjoy the rest of your day. Hopefully you found this helpful.
Yeah. Thank you, James. Thank you, everyone. Please reach
You're welcome.
out to tsdat@pnnl.gov if you have any questions.